our portion is filling of orbitals in atom. That means the filling of electrons in the atomic orbitals, that is 1s2, 2s2, 2p6, like that. This filling takes place on the basis of certain rules. So, the filling of electrons into the orbitals takes place according to Aufbau principle, which is based on Pauli's exclusion principle, Hund's rule of maximum multiplicity, etc. First one, we studied about Aufbau principle. Aufbau is a German word, means building up. So this principle, otherwise known as building up principle, Aufbau is a German word which means building up. The principle states that the electrons are filled in various orbitals in the increasing order of their energies. This orbital with the lowest energy will be filled first, and then the orbitals having highest energy. So first the lowest energy, finally the highest energy orbitals are filled. So on the basis of this Aufbau principle, we can fill the electrons like this. It is 1s. So the principal quantum number or main shell n is equal to 1 indicate K shell. So 1s. S is a subshell. So 1s first filled because it's having lowest energy. Then second 2s. The increasing energy order 2s, then goes to 2p, then 3s, then goes to 3p, 4s, then goes to 3d, 4p, 5s, then goes to 4d, 5p, 6s, then goes to 4f, 5d, 6p, 7s, and then goes to 5f, 6d, 7p, and continue. So this is the increasing order of the energy level of orbital. So you remember, in the case of s orbital, only one possible orientation in space. So s subshell or s orbital having maximum number of electrons accommodated become any s orbital maximum accommodation of electrons are 2. Then in the case of p orbital, p having 3 possible orientation, px, py, and pz. This px is on atomic orbital, this having maximum electron 2, then 2pz, and also 2, then maximum in p subshell, maximum electrons accommodated are 2 plus 2 plus 2, that is 6 electrons are accommodated. Then in the case of d subshell, d maximum possible orientations, 5 possible orientations, dxy, dxz, dyz, dx square, y square, dz square. 5 possible orientation in this atomic orbitals, 2 electrons, this also 2 maximum 2 electrons are accommodated. So maximum in d orbitals, 5d orbitals are there, in 1 2 electrons are accommodated. So maximum 10 electrons. 10 electrons are 2 plus 2 plus 2 plus 2 plus 2. 10 electrons are accommodated. Then f orbital, it is a highly complicated structure, so complex structure. So f orbitals having, we know, 7 possible orientations. So in one orbital 2 are accommodated. So maximum number of electrons is equal to 14. So in the case of s orbital, 2 electrons, p 6 electrons, d 10 electrons, and f 14 electrons. Now we study how to draw this figure easily. Right, 1s. The next one, a space. A space is there, leave it. Then 2s and 2p. N is equal to 2 subshells are there, 2s and 2p. Then this not write exactly down, then one space, then bottom to 2p write 3s, 3p, 3d, because n is equal to 3, then 3 subshells are there, 3s, 3p, 3d. Then leave it the exact bottom portion. Then in the bottom of this 3p write 4s, 4p, 4d, 4f. Then this leave it this bottom portion, then write 5s, 5p, 5d, 5f. Then leave it this bottom portion, then write 6s, 6p, 6d. then this leave it this bottom portion, then 7s and 7p. It is continuing. Easy to draw. We limit this up to 7p. Then the electrons are accommodated in 1s. Then the electrons goes to from 1s to 2s. Electrons, then 1s, then 2s. From 2s to 2p. 2p to 3s. From 3s to 3p. From 3p to 4s. 4s to 3d, then 4p, then 5s. Then from 5s to 4d, 5p, 6s. Then 6s to 4f, 5d, 6p, 7s. And from 7s to 5f, 6d, 7p, and continuing. So, by the increasing order of their energy level, the filling of electrons takes place according to Aufbau principle. The next rule for filling of electrons are Hund's rule of maximum multiplicity. Hund's rule of maximum multiplicity. So, in the case of degenerate orbitals, the electrons are first singly filled, then only pairing takes place. We can explain this with the help of an example. You know, nitrogen atomic number 7. We can write the electronic configuration 1s2, 2s2, 2p3 because total 7 electrons are there. S orbital maximum 2 electrons, another is any s orbital maximum 2 electrons are accommodated because it's having only one possible orientation. Then 2p3, in my hand only 3 electrons are there. These 3 electrons are accommodated in this p orbital. So, this is SPDF method of electronic configuration writing, and this is the orbital diagram method of electronic configuration writing. That is like this. Put it in a box, 2 electrons. One is in clockwise direction, another is in anti-clockwise direction. Then in 2s, only one possible orientation. So, one box, one is in clockwise, another is in anti-clockwise. 2p3. In an atomic orbital, px is an atomic orbital, we know maximum 2 electrons are accommodated. In my hand 3 electrons are there. So here in 2p3, 2 possibilities are there. These electrons are accommodated like this. 2 electrons, maximum 2 electrons are accommodated here. Remaining 1 electron is accommodated here. This is one possibility. The next one is 3 electrons are accommodated one by one in 3 degenerate orbitals. What do you mean by degenerate orbitals? The atomic orbitals having same energy. These, you know, these px, py, pz all having same energies. Atomic orbitals are known as degenerate orbitals. So, in the case of degenerate orbitals, this is the correct answer. So, the electrons are first singly filled because they are having same energy. So, the electrons are first singly filled, then only pairing takes place. Then the remaining electrons are there, then only the pairing will takes place here. So, 3 electrons are first singly given and then only pairing takes place. This is the incorrect option. So, in the case of degenerate orbitals, the electrons are first singly filled, then only pairing takes place. Another example in the case of oxygen, atomic number 8. Then in this case, we can write 1s2, 2s2, 2p4. Then in this case, the orbital diagram method for this 2p4, 2p, 3 possible orientation, px, py, pz. In this, in my hand 4 electrons are there. First, according to Hund's rule, first I will give singly 1 electron for this orbital 1. Then remaining 1 electron is there. Then I will pair it. Clear? So, first in the case of degenerate orbitals, the electrons are degenerate means same energy level. The electrons are first singly filled, then only pairing takes place. Next one is the Pauli's exclusion principle. The principle states that No two electrons in an atom can have the same set of 4 quantum numbers. That means you know 4 types of quantum numbers are there. What are they? Principal quantum number, subsidiary quantum number, magnetic orbital quantum number, and spin quantum number. So, you know in an atomic orbitals maximum 2 electrons are accommodated. Then 2 electrons are in an atomic orbital. They cannot have the same set of 4 quantum numbers. That means in an atomic orbital 2 electrons are present, then they must have opposite spin. You know spin quantum number gives the spin of electron. In an atomic orbital 2 electrons are there, then one is in clockwise spin and other is in anti-clockwise spin. That means one having the value plus half and other will have minus half value. No two electrons in an atom can have the same set of 4 quantum numbers. That means the spin quantum number will differ. One having plus half value and the other having minus half value. It can also be stated as an orbital can have maximum 2 electrons and they must have opposite spin, plus half and minus half. That means they will differ. This is known as Pauli's exclusion principle. No two electrons in an atom can have the same set of 4 quantum numbers. Which quantum number will differ? Definitely spin quantum number will differ. They must have opposite spin. Next our portion is the stability of half-filled and completely filled subshells. In the electronic configuration of chromium, you know chromium atomic number 24, the electronic configuration is 1s2, then 2s2, then 2p6, then goes to 3s, 3s2, then 3p6, then 4s. 4s, you know s orbital maximum 2 electrons are accommodated, then goes to 3d. 3d, the remaining electrons are 4 accommodated in this 3d level. So this is known as SPDF method of electronic configuration, and this is known as orbital diagram method. A box is there, then how many electrons are there? One is in clockwise, other is in anti-clockwise. So 2s2, 2p6, 2 electrons, then 3s2, 3p6, 6 electrons, then 4s2. This electronic configuration 4s2, 2 electrons are accommodated. 3d4, 3d4 according to Hund's rule, this is degenerate orbital, same energy level orbital. So first singly filled, 1, 1, 1, 4 electrons are over, in my hand 4 electrons. So in this case, from this 4s level, 1 electron jump 3d level, because this type of configuration is more stable. Original configuration is then 4s1 3d5. Then here the 1 electron, here only remaining 1 electron is there, only 1 electron jump from this level. Degenerate orbitals having single electron. This configuration is more stable, so 1 electron jump from this level to this level. This is known as, you know, d orbital maximum 10 electrons are accommodated, maximum d10, but here only d5 configuration is there. That means half filled d subshell. Half filled configuration, this is more stable compared to that of the previous one. Then we can discuss another example in the case of copper. Copper atomic number 29, we can write the electronic configuration in SPDF method. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. The remaining is 9. Then in this configuration also 4s2, 3d, according to Hund's rule, first singly filled 1, 1, 1, 1, 1. Then remaining in my hand 4 electrons are there. This is paired. Then one orbital with only 1 electron. So from this 4s level, 1 electron jump to this 3d level. So here also 1 electron from this 4s level and 10 electrons, 4s 1, 3d 10. One electron also jump from here and here also paired. So the completely filled, you know, d orbitals having maximum 10 electrons are accommodated. So here 4s 1, 3d 10, 3d 10 configuration 3D, that means completely filled d orbitals. This configuration is more stable. So half filled and completely filled subshells are more stable. So this is due to the following reasons. First one, the symmetrical distribution of electrons. That means in this case, symmetry, all having one electrons. That means symmetry, all having one electron. These d orbitals are degenerate, all having one electron. This is here also all having 2 electrons, symmetrical, 2. Same number of electrons are accommodated in this subshell. So this is known as symmetrical distribution of electrons. So due to this symmetrical distribution, this configuration is more stable, D5 or D10. Then the second one is exchange energy. The second one is exchange energy. The electrons with the same spin present in degenerate orbitals. Electrons with the same spin. Spin means, you know, in these all electron, one electron in this orbital, one. These electrons are having time. So the electrons in the degenerate orbitals with the same spin have a tendency to exchange their position. Sometimes it may go to this one and this goes to this side, or because they all having same energy, degenerate orbital. So at that time energy is released. The positions are exchanged, then the energy become released. That energy is known as exchange energy. When the amount of exchange energy is maximum, then the stability also increased. So in the case of degenerate orbitals, the exchange energy is maximum, hence they are more stable. So degenerate orbitals, they exchange their positions, then the releasing amount of energy is more, so they are more stable. So these are the two reasons for the half filled and completely filled electronic configurations are more stable compared to the other one, because first one symmetrical distribution of electrons, second one exchange energy. Next, our portion is the electronic configuration of atoms. You know how to write the electronic configuration. What do you mean by electronic configuration? The distribution of electrons into orbitals of an atom is called its electronic configuration. The electronic configuration can be represented by two ways. First one, we already know, SPDF notations, that is 1s2, 2s2, 2p6, like that. That is known as SPDF method of writing electronic configuration. Then, for example, hydrogen atomic number 1, then we can write the electronic configuration as 1s1. Hydrogen atom 1 electron, this electron is represented like this. Helium atomic number 2, then the electronic configuration is 1s2. This type of electronic configuration writing is known as SPDF notation of electronic configuration. Then next one, orbital diagram method. In this method, you know hydrogen 1s1, then draw a box, then that one electron is represented like this, like an arrow. This is known as orbital diagram method. Then for example, helium, you know the SPDF notation is 1s2, then S orbital only one possible orientation, so one box, then one is in clockwise direction arrow, other is in anti-clockwise direction arrow. These represent 2 electrons. Then lithium atomic number 3, then electronic configuration SPDF method 1s2, 2s1, total 3 electrons, 2 plus 1. Then S orbital only one possible orientation, one box, 2 electrons, one is in clockwise, one other is in anti-clockwise. 2s1, 1 electron, so this is in clockwise direction. So two types of electronic configuration representation, SPDF notation and orbital diagram method.